Sir, your voice is cracked.
Hello, am I audible to you guys?
Yes, sir.
Yes, sir.
Yes, sir.
So I think last lecture we did some of the numericals for Newton's laws of motion, and yeah, we saw the falling stick problem. I think that was the last question, right?
Yes, sir.
The falling stick problem, we saw two different cases. One was the hinge case, and other was the friction. In case of hinge, it was the two-dimensional force Rx Ry that we apply at the hinge. And in fact, without applying the hinge erection force, we apply the torque method about the hinge to get the answer. We also realized that the acceleration of the rod was in the direction perpendicular to the rod because we were releasing that. We never considered the motion of the rod. So it means we assume that in every situation, the object was released from rest. So omega was totally ignored. Now, as a consequence of this ignorance of omega, we made sure that there is no centripetal acceleration. That is, the omega square r term was not part of our calculation. So, only thing that were there was tangential acceleration, and that was very easy to calculate using the torque method. Now, I mean, of course, you will not come across such situation very often. It could be possible in JEE Advanced, but for any other examination, including NEET, I mean, please do not expect a difficulty of that level. So you can totally skip this particular problem, in which the omega is also there. So here goes the next question, and this is fairly challenging. So just for the sake of this clarity, that what went, I mean, what can possibly go wrong if you come across a situation like this? So imagine we have a rod which was vertical in the very beginning, and then later on, after falling through some angle, it has gained some angular velocity. So that is quite possible. So this is when omega is 0. So it starts falling. So here omega is 0. And after traveling some angle theta, now the rod is having omega. And now let's say you're trying to analyze the situation. So it will be really complex and it's not going to be very easy. So I may assume that let's say the bottom is at rest. So bottom is not slipping anywhere. So let's consider bottom is so that's the other way of saying that the friction is sufficient for this to prevent. And now we can draw the FBD, which is fairly simple in this case. So we can just draw the normal here at the bottom. And the gravity will act at its usual place called center of gravity or center of mass. You can take its uniform gravitational field. And then there is no force. So now the torque method only gives the centripetal acceleration. Right now things are not very simple. So why it is not simple? Because the center of mass in this case is having, because this bottom is like a fixed point, therefore bottom is like a center of circle, or it is this way actually. Can you guess the path of the center? And it turns out to be yes, you can guess the path of center. It is a circular path, correct? And where is the center of that circle? The answer is it is
Bottom.
And because the path of the center of mass is circular, so it's a circular motion problem. So every problem we analyze by looking at the center mass motion, and because here the center mass is trying to move in a circular path, so we have a circular motion. And the point is the center mass that we'll discuss about. So we'll choose the center mass as the point of interest and we discuss about it. Now this will have two different acceleration as we know. So it will have one tangential like this. Another will have centripetal axis. So now this tangential acceleration we call it just A, and now this is omega square L by 2. Now these are the two acceleration. Okay. So now the laws of motion will be quite different. It is not going to be same as before. So because we have accessing two mutually perpendicular actions, so there are two possibilities. Either you write the net force in these two directions, or you resolve these forces along horizontal and vertical. Sorry, resolve these acceleration along horizontal and vertical, and then write the law of motion. So what I'll do is I'll just show you both of them. So now mg, what is the component of mg along tangential action? So I'm trying to write f net ft equals to m into 8, and I'm going to write next is fc equals to m into s. Okay. So let's begin the first part. So what is the force acting along the tangent? Okay. So it won't be very difficult because the normal and mg, normal is acting upward, mg is acting downward. So the net force I can take as mg minus n acting downward. Okay. And then take the component, which is sin theta. Is this clear? Probably no. Huh? You can bring the
Yes, sir.
normal here, right? Bring the normal here at center of mass, and then take the component. So this is theta, this is theta. So mg sin theta is supporting and n sin theta is opposing, isn't it? This is the n sin theta, right? And this is the mg cos theta. Okay. So now this is the net tangential force, and this will be must equal to m into a, or m into a, just because I'm writing a as a at value. And the other equation, okay, no, I missed one more thing. I missed one more. So I should have taken care of this. So here the friction force is also there, which I totally missed. Okay, so the friction force must be taken into consideration. So what about the friction? So now this part is okay. So the coefficient of friction in the direction of acceleration is how much?
Fs cos
This
theta.
is f. Yeah, this is f,
Fs
and
cos
it is
theta.
support. So mg sin theta plus fs cos theta minus n sin theta equals to m into a. Fairly complex, but yeah, it is something complex only. Again, why I'm saying this, because this is just to make sure that you understand what is happening in situation like this. And net force on the centripetal force will be how much? So that's mg cos theta minus n cos theta, because that's opposing. And fs will have sin theta again minus
Fs.
equals to m omega square L by 2. So these are the equation, the way of writing the equation. Okay. Also, we can write the torque equation. So the torque equation about which point we can write. Okay, so we can write the torque about the bottom. But in this case, I mean, it is not advisable to write the torque equation because it's some accelerating body with some unique velocity, angular velocity as well. So probably things will be slightly difficult. But anyway, in this case we can apply. So torque about O equals to I about O into alpha because we are looking for alpha. Alpha is pretty easy to find. So torque about O is how much? It's the same thing. Mg sin theta into L by 2. That is the torque about O. Normal will have zero torque and everything else will have. Now this point is in the okay, the center mass is having the acceleration omega square L by 2. O is having acceleration in the CM frame omega square L by 2 towards the center. It's just the other way around. So if you look from the center mass to the point point O, it will accelerate towards it. Right now we are looking at center mass with respect to O, it's towards O actually. Anyway, but this is simple. And I about O is ml square by 3 into 1. So this part is simple, this part we know. Alpha was 3 by 2 g sin theta by 8. Okay. And because we know alpha, so in fact we know A in a way, A is alpha, which is 3g by 4 sin theta. Okay. So later on when we will learn the energy method, we can do this by energy method easily. So whenever we have the angular velocity, we prefer energy method instead of logarithm. So we'll see that part in the next part. So the whole idea is the moment omega comes into the picture, you have to think this way. You have to think of centripetal and tangential both. When we release a body from rest, you're lucky. It is only tangential. Okay? So alpha is not the only acceleration. It could be the centripetal is totally something that we totally miss. But you can come across a situation like this, and then you have to think more deeply. Anyway, so let's leave this question. If you come across question while solving, you can discuss in class continuation. The last question from the falling rod problem. For frictionless volume. So what if the friction is zero?
So the
Then
center of
correct.
mass will travel in a vertical path.
Correct. In this case, the center mass will
Downward.
directly downward. There is no option to go right or left. So now the acceleration of center mass will be this way only for sure. And definitely the normal will act like this, which will produce the alpha. And then we can add the logarithm quite easily. So the net force is mg minus n equals to mac. That's it. And the torque equation about center. So we'll take the torque about center mass because the bottom is not at rest, rather it is slipping left. So torque about center mass is how much? Tell me what is the torque about center mass? Okay, assume this angle is theta. So let me take this. Tell me. So who will provide the torque about center mass? It is the normal one.
Mg cos theta.
I'm saying torque about center mass, and center mass will have this much torque. So this is equal to m L square by 12 into. So now, in a situation when the point is not like acting as a hinge or a point at rest. You should not take the torque about that point. In all such cases where you fail to see the hinge or ICR or a point at rest, it's always good to go with a torque about a center of mass, because that formula is always correct. I tau Cm equals to ICM alpha. So I will show you later on why this is always true and not the other way around. Okay. So this equals to yeah. So now we can solve L by 2 cancel. So n turns out to be m alpha L by 6 plus. Correct. And the question is how to relate the alpha with AC. Is there any way to denote the alpha with AC? The answer is yes, there is a way. That's not very difficult at all. The reason is we know the bottom is trying to slip left and we can see the ICR. Can you see the ICR? In this falling rod form, this is ICR. This is ICR. Because the bottom is trying to slip left and the center is trying to go down. And if you draw the perpendicular to the velocity direction, you can see the ICR very easily. And because this is ICR, you can easily write alpha into the separation from the ICR to the center of mass equals to AC. AC is how much? Alpha into L by 2 cos. Can you see that? So we got the AC as well. And therefore, you can solve this entire equation. So it's totally solvable. But there is other way around you can also derive. So the kinematics part is easy because this is kinematics. It has nothing to do with the rotational dynamics. So bottom is trying to go left. All right. It is bottom will have zero acceleration in the vertical direction. Correct. And the acceleration of center mass is AC. And the rod is turning this way. So imagine that you don't know about ICR, still you can do this. Because the acceleration of every point of the body will be having one component which is same as center mass acceleration. So the AC is given to this point. If AC is the acceleration of center mass, then this is the acceleration for every other point. But apart from this, in the frame of center mass, you can also see one extra acceleration. And what is that? In the CM frame, it is always having the acceleration, which is centrifugal. Okay, now again here the same question. The omega we are taking as 0, so we are releasing from rest. Because if this is not the case, then things will be really complex. Okay. So now in the CM frame, this point will go in this direction with alpha L by 2. And the acceleration must be towards left only because it is slipping towards left. So all the vertical component must cancel out each other. And to cancel out the vertical component, you can see the AC must be equal to alpha L by 2 cos. Since bottom is slipping towards. Therefore, no vertical. Understood. So what we are trying to do is we are trying to make the vertical component 0 to get the constraint relation. So these are fairly difficult problem, and if I bring the omega, then this becomes the super difficult. So anyway, that is not going to be of a part of any numerical solving. Okay, I would like to discuss one problem which I thought to discuss in the torque part, but somehow I missed. But it's never late. So let's discuss the part. So we have a wall. And let's say this is a brick of mass and dimensional, let's call it A and says B. So this is A and B is the dimension of the brick. And the brick is pressed exactly at the center by the external force. And friction is sufficient. This is a rough surface. This is wall. So friction is sufficient to prevent slipping. This force is acting at the center. The question is, where the normal reaction will act on the brick? Will it act at the center on the left, above the center, or below the center? If it is not at the center, then how far from the center? That is the question. Once again, will normal action will act here or above or below? If center, then it's okay. If not center, then how far? That's the question. Clear? Questions clear?
Yes, sir.
Because the normal action will act. First question is where they should act, and the second is if it is not acting at the center, then how far from the center it is acting. So we need to know the x value. So that's the question. Okay, so question is I think clear. So I can how to put in words. Find the distance of normal reaction with respect to center of. So what you will do is you can think as I talk about the because it's a body with dimensions, it's not a particle. So earlier when you used to do the FBD, it was really meaningless or somewhat of no use to think about the location of normal reaction. But if you remember my words in the chapter, I said that normal is a distributed force and it is the property of the distributed force to act at a point where it is trying to balance the things like force and torque. So now About center mass, okay, how friction will act by this? If you draw the ability, let's draw the ability. So mg is fixed because you can't change it.
So friction will act upward.
And the friction will act upward. So let's write fs mg. Now only first left is normal direction. So
So
what
we
are
can
the
take n as a distance x, and then we can calculate by using
yeah
torque equation.
correct. So the n should be below the center or above the center.
So we can take anywhere, and then value of x will give that answer. It is
Yeah.
below or above.
But organically you can see that is correct that you can take anywhere. But can we actually see it where this should be without thinking of the equation? The answer is yes, we can see it. And how? So look at the torque of the forces that you can see right now. So about center mass, mg will have zero torque, f will have zero torque because f is also passing through the center mass. If we
Yes,
extend the
sir.
f, so the only torque is the torque of static friction, and the static friction will try to turn the brick clockwise. So now to prevent the brick from turning clockwise, the only way is to provide the torque anti-clockwise. So
Yes, sir. So it
above
will
center mass, we want anti-clockwise torque, so the above must
so
be below.
below.
And the simple question is Fs into A by 2 is n into x. And therefore, n turns out to be, sorry, x turns out to be how much? And you can put the Fs value because for equilibrium, Fs equals to mg also. F equals to n also, you can always write F equals to n for translational equilibrium. And therefore, you can substitute everything here. So you can say Fs equals to uh, mg A by 2 and n equals to f because that's the equation, and therefore the x turns out to be mg a by. You can find the distance of the way normal should act. Okay. And then there is a very nice problem in SC Verma. Probably I don't remember the question number, but I can tell you this question. So if you have SC Verma, then it's good. The question is. Uh, Anyway, I'm not finding the question, but let me tell you the question. What is this question, which I remember? The question from this one is like we have an inclined plane and there is a block of certain dimension. It's a very similar to the brick problem, but there is some difference. And what is interesting given here that this brick or this block is actually accepting not does not is not accepting the node, rather it's moving with constant velocity. The constant velocity means net force is zero. So you know how much friction is active. Mass is n, and let's say the height is h, and the base is b. So the question is find the torque of normal. Find this was a question of S Verma, but let's modify this. Also find distance of n with respect to center. So S Verma has asked the first part, but you can also add the second part. To solve this question, meanwhile I'll search it. It was I have seen this before. Yeah, I think I got it. Yeah, this is question number 21. So if you have a circle, I can see it. Maybe you have solved this in tutorial. So now what you need to realize that if a body is moving down the plane, it's a body, it's not a particle. So always thinking that the net force is zero is not sufficient. Why? Because if it is slipping, then the friction will be acting up the plane for sure. This is the Fk because it's moving down. And it is also given that it is moving with constant velocity, so which means the Fk and mg sin theta is definitely balanced. So the translational equilibrium part is discussed, but if you look at the center mass, we know that the kinetic friction will create a torque about center mass in a anti-clockwise sense. So if we assume that the normal is acting exactly at the center, the brick or this block must topple on the main this surface. So to prevent this torque, the normal direction is only for left, and that must create a anti-clockwise, clockwise torque to balance it. And for that reason, the normal must be acting somewhere below the center. And you can see again the x is there.
So x is tan theta into h by 2.
Yeah. So finding the n is pretty easy. The torque of the first part is simple because torque of normal is exactly same as the torque of friction. So that's why they are balancing out. This is same as torque of friction, and the torque of friction is how much? Fk into h by 2. And the Fk is mg sine theta. In the given SVM problem, they have written says h as a small a. And now finding the x is also easy, no? Because we can add n into x equals to Fk into h by 2, which is mg sine theta h by 2. And the normal is equals to mg cos theta for equilibrium. So mg and therefore mg will cancel. So x turns out to be h by 2 tan theta. This is a really interesting problem that we can create out of nowhere. So this was important, and I wanted to discuss actually just for that. So understood. In case of body, you have to be very careful. So the forces which you are sure it will act this way, apply it, and for other forces you have to think logically that what and how it should be applied in order to balance it. Now this issue I was facing a lot while cleaning the blackboard or the whiteboard using duster. So duster used to topple a lot, like it will slip out of my hand, will jump many times because of this particular reason. If my force is not, if I'm not holding the duster properly, it can slip easily because of the torque of friction. So you might have seen your teachers trying to rub the whiteboard or blackboard and the duster is slipping out of the hand. Anyway, so this question was important, and then there is some variety of question that one should know. And this is called the step Pulley problem. So what is step Pulley? So it's a pulley, and then we have another pulley. You can see this is one pulley. And then we have another pulley. So it's like a cylinder of a decreasing radius. And then from here you can go one more further, like and now it is well supported by the some sort of axle. So the center is can turn like this, and you can hang object from different cylinder. So when you look from the front side, if you look from this side, you won't see this way. What you see is the concentric rings. So that is how it is drawn in a notebook. So this is the diagram of the step pulley, which you see very often, and this is the center is hinged. So it can turn either clockwise or anti-clockwise. That's the question. And then we have strings attached to different pulley, as you can see. One I'm attaching here, then I'm attaching here, and I'm attaching here. You can see for with every pulley I have attached one thread, and let's attach some mass. This could be any value, maybe m, not less m1, m2, m3. Now, depending on which one is having the like the net torque, it can turn clockwise or it can turn anti-clockwise. I don't know how it will turn. So tell me how you want to assume, clockwise or anti-clockwise. So the entire pulley can turn either way. It cannot turn both way because it's a one single structure. It will turn clockwise or anti-clockwise. So which direction you want to choose? Tell me.
Anti-clockwise.
Clock.
Yeah. Because it is alpha. Now, if this is the alpha, then how M3 will go? Okay, now they will give you the radius of each. Yeah, so radius of each pulley will be different. Maybe it could be A, B, and C. So, what is the accession of M3? If alpha is the accession assumed, how M3 will go? It will go down or up? M3 will go down or up,
Down.
and the
Yes.
accession will be alpha into C.
Yes, sir.
What about M1? M1 will also go down, alpha
Yes.
into A. M2 will go up, alpha into B. So I think the
Yes.
accession part is pretty easy. You can see that we don't have too many variables. In fact, we have very less variable, and the entire pulley will have the moment of inertia I because it's a step pulley, so it's not something which you know. This I the moment of inertia, and then writing is very easy. Three strings, so three tension T1, T1, T3. This is what's called T1 and T2. Now, which the tension which supports the alpha will be positive torque, and the tension which opposes the alpha will be negative torque. So the way of writing the question is pretty easy. T3 into C plus T1 into A minus T2 into B net torque. I hope this is clear. Equals to I alpha. That's it. So for pulley, this is the equation. The net torque about the center equals to I into alpha. That's it. And then now we have the three separate blocks, and you're supposed to add the equation. So it's easy. You can add M3 minus T3 equals to M3 alpha A alpha C, alpha into C. And M1 G minus T1 equals to M1 alpha A, and what? The last one. It's going up, na?
Yes, sir.
So T2 minus M2 G equals to M1, no sorry, M2 alpha B. So what you can do, you can substitute T1, T2, T3. So find T1 from this, T2 from this, T3 from here, and put in the equation 1 and solve, and you look at the answer for alpha. And it's done. Okay. So this is a step pulley problem. So it's not very difficult.
have the note there.
Pardon?
So
You want to note it? No.
it's a noted, sir.
So we have seen a lot of variety of laws of motion problem. So now we'll see something interesting. So what is that? So we have a disk, and this is purely kinematics. So we have a disk, a uniform disk, and this is the axis. So what we are doing is we are just putting this on a ground. Okay, I'm trying to create something. Okay, so what I'm trying to do is that this block is, sorry, this disk is given a spin omega naught and release on a rough surface. So it is spinning on a rough surface. Okay, so that is the case. So once you put on a rough surface, let's say the radiuses are. So what do you think? Will it speed up or slow down? If you spin a disk and put on a surface,
It will slow down.
it will slow down. That's simple. And because it will slow down, so the question is after time t, what will be its angular velocity? Let's say the angular velocity in the beginning is omega naught. So this is the question of kinematics and dynamics both. Now, what is difficult here to understand what is the torque value? So friction will oppose, but how the friction will act? So if you cut a small piece of disc, you can easily realize that every point on the disc, I mean, sorry, on this ring is trying to move tangentially. So friction will oppose tangentially only. So friction will act like this, something like this. It will be tangential everywhere. And because the friction is tangential everywhere, so the net friction force will be zero. So it will never create the centripetal, sorry, it will never create the acceleration of center mass, but it will create a torque. And to find the torque of this part is easy to write that d tau about the center, about this O, is df, the friction force into radius at which we have cut this radius. Let's call it r. So force into r. This is pretty easy. And now how to find the force? It is equals to mu into dn. Why dn? Because the weight of that ring will be small. So that will create a small. And is equals to mu into dmg. dm. And that's easy. So now you can add. So let's find the torque first. Mu and the dm we can add as proportional to area sigma 2 pi r dr into g into r. And now we are done. Sigma we can substitute later on because we know everything of sigma. So mu into sigma into 2 pi into g. And what we have left is r square dr. And now we integrate. So the net torque of friction will be sigma 2 pi mu g r cube by 3. And sigma we can write as m by pi r square. So the answer is 2 by 3, 2 by 3, right? Mu m g r. This is the torque. Now the first part is done, which is the torque part. And the next part is omega. So that's a different story. So what we can write, because this is the opposing torque, so we can write the retardation produced will be equals to torque upon I. And why minus n? Because it's opposing. So alpha equals to minus 2 by 3 mu mgr. And the moment of inertia of this about the center is m r square. So again, this will cancels out. We get alpha equals to minus 4 by 3 mu g by r. Okay, and this is constant. That's interesting. So this is constant value, and of course it will be constant as long as it is slipping this constant. And therefore you can use the kinematic equation easily. So omega equals to omega naught plus alpha t, and alpha is negative, so we can see clearly that omega as a function of time t will be this much. So they may ask you after what time it will stop. So when base will comes to rest, you can write omega equals to 0, which implies t equals to so questions like this will be also part of your discussion. So you need to understand that when we have tangential forces, you just need to multiply the net force value. It's something very weird that we are writing the net force. Basically, in a sense, it happens, and then you add the all torque to get the net torque. Okay. So here every force is contributing in a equal sense. That's why the DDF, like it's like elementary and elementary further. So it's, I mean, how to say this? Very lengthy concept. This is a disk which is spinning. Yes, yes. So what you're trying to do is you're trying to make a small elementary ring, and this elementary ring is turning clockwise. So the tangential force will act everywhere like this. Now, the force acting on the entire disk, if I say dfk, then this will be like a, this is like a d of df. I can just take a small piece of this ring also for the. Okay, so D, if I say this is a small piece, what is the force acting on this piece? This is R, this is, let's say, d theta, and this is dr, the thickness of this ring. So we can say the area dA will be R d theta dr, and therefore the dm will be sigma R d theta dr, and therefore the d of df, like the elementary of elementary. So I'm taking first elementary as a ring, and then I'm taking one more elementary as a, like a dice, like a square, maybe something rectangle, you can say. And it turns out to be mu dmg. This is the friction force acting on that part, which is the elementary of element. And this is mu sigma r d theta dr into g. This is the ddf, the friction force on the elementary of element. And then the torque, the d tau, if you just calculate, the d tau will be equals to how much? Df into r. And this turns out to be mu sigma r d theta dr into g into r. And then if you just integrate the theta from 0 to 2 pi, so let's integrate first. So once you integrate only for theta, so don't consider for r. First we integrate for theta to cover the entire ring. So d tau will be d of d tau, and that is equals to, I'm just taking r part outside, r square dr outside, g outside, only d theta part. And if you do so, the theta will go from 0 to 2 pi. So the first integration gives you d tau, which is 2 pi sigma mu g r square. And now you integrate for the r part, because we have done for the integration for the ring. Now we can integrate one more time, and this will integrate from 0 to capital R to get the net. This is the actual way of doing it, but you can do the way I did earlier. So that's easy. Okay. So if you want, you can do this way also. There is no limit of elementary. I can take elementary, I can take further elementary, I can take further elementary, and then I will start from the innermost integration to get the next part. Then again I will integrate to get the next part. Then again I will integrate to get the next part, and so on, so on. So I can keep on doing this integration maybe infinite times, because I'm taking elementary of elementary of elementary of elementary of elementary. I mean, it can be infinite loop. Okay. So anyway, this is the one question which you need to know how to attempt. So we'll do one problem with the, just to recall back the spring property that we did earlier in laws of motion. So we have a plank of mass m, length m, and then we have a ceiling support. Now this plank is suspended from the ceiling with the help of a spring, identical spring. So both are identical spring. And because this is at equilibrium, so I hope that you can understand easily that the weight of the plank must be balanced by the spring force, right?
Yes, sir.
So now, if I remove one of the spring immediately, then what will be the acceleration of center mass?
The spring phase doesn't show change.
Correct. So even if you remove one of the spring, the other spring force will remain, sir, isn't it? So finding the acceleration of center mass is pretty easy job. You can find the acceleration of center mass. You can also find the alpha of the rod. You can find the ACM and alpha just after cutting one of the spring. Find ACM and alpha of plank just after cutting of one spring. Now, when I'm saying cutting one spring, it means I'm totally removing it, so it's not anywhere connected. So how we denote this? We denote like this. It means remove the entire spring, not the upper or the bottom part. Earlier, if you remember, I should do like this, right? Which means I'm cutting up, I'm cutting down, but now I'm cutting both. So that's how we denote it. So what will be the answer? Tell me. 'Anybody solving this question?
Yes, sir. Sir, just 3G by L.
3G by L.
Yes, sir. Alpha is 3G by.
Okay. 3G. So let me check. So the spring force was how much? The spring force was mg by 2, right?
Yes, sir.
And mg by 2 into L by 2 is the torque about the center mass after the cutting part, because other spring is gone. So this is the only torque, equals to ml square by 3, sorry, by 12 into L. This is what you did, right?
Yes, sir.
And what about the the acceleration part?
Yes, sir. Don't forget me. 3 by 2G.
Okay. Yeah. So this is this, 3. And for the center mass, it's mg minus kx, which is mg by 2, is ma. So for the obvious reason, this part is obvious reason, because the spring force is still mg by 2, because once you cut it, the spring force cannot change its value instantaneously. So it will take some time. So the answer is G. So now you have the alpha and you have the ACM. Can you tell me what is the acceleration of this point? So what is the acceleration of P? I want to know the acceleration of point P. So what will be the answer?
Why we didn't use ACM is equal to alpha by alpha into L by 2?
Correct. ACM plus alpha L by 2. So G by 2 plus alpha L by 2 is how much? Alpha L by 2 is 3 G by 2, which is 2G. The point P will accelerate downward with accessing 2G. Okay.
So I was asking for the first case, why we didn't use alpha is equals to, sorry, ACM is equals to alpha L by 2 for the first case.
Okay, because that point is not at rest. So this point will accelerate now. This point is not fixed. No?
Okay.
Because the spring will let it move up or down both. So spring is not a constant relation, right? Tension is constant, normal is constant, but spring is not constant. If you remember, spring force is not put into the category of constant force, and therefore you cannot apply the constant relation when spring is present. That's a very interesting part which you have raised, and everyone should hear. Remember this fact that the constant which you used to write earlier will not be true now. Okay. So with string, we had written the constant relation because string cannot be stretched. But with spring, it is possible to stretch, and therefore the point cannot be taken as a point which will have zero acceleration. So it will have some acceleration. Okay.
Yes, sir.
All right. So now we can do something even more interesting with the same problem. Oh, sorry, I was mute. Okay, so the question is simple. You have a two identical spring. We have a plank of mass capital M, length L, and a small point mass is kept at a distance of L by 4 from left string. Okay, so I'm calling the string 1 and 2 as the name suggests, and then I'm cutting the string 2. And what I'm asking is, once I cut the string 2, what will be the changing tension of the string 1? It means it must have some initial tension which we don't know. in which you can figure it out. And then what is its new tension? Okay. And then what is the changing tension? So for the sake of simplicity, let's take m equals to 3m. This will ease out your calculation, hopefully. So take m equals to 3m. And the block is a dimensionless object, so it's having a point mass concept. So the m is a point mass which is kept on the plank. So you remove the or you cut the string 2, and then just after cutting the string 2, you're supposed to find the changing tension in the first string. So if you are interested, you can take some time to solve. You may take 10 minutes to solve this question. It's really challenging and worthy of solving. So anybody interested in solving this question?
So So when we cut the string 2, the both mass m and 3m will fall independently now.
Yes. So m and 3m will have no resistance. They are independent.
So is it 3 mg, 3 small mg?
So the first equation will be you have to do the everyday plan 3 mg tension and the normal here. So the equation will be 3 mg plus n minus t equals to m 3m into A of the plank. So I'm taking the acceleration of center mass of plank as A. And then you write the torque equation about center mass. So T into L by 2 is trying to turn clockwise minus n into L by 4 yeah, about center mass, and this equals to I into alpha, which is m. Now the block will have mg here and normal. Now we need to find the acceleration of this point P in terms of alpha and A. It will be A below and alpha L by 4 above, right? So the net downward acceleration will be A minus alpha L by 4. This you need to realize from kinematics of that point, because that point is part of the plank. So the block will fall along with the plank, and therefore it will have acceleration equals to A minus alpha L by 4, and therefore because it's going together, so it will have same acceleration. And now the equation will be mg minus n equals to m A minus alpha L by 4. So these are the equations which you need to apply and solve. Not very easy, but indeed it's challenging problem. So this also helps us. I mean, you realizing that you cannot add the weight of the block on the plank. So generally, it happens that what they most of the students do, they add the mass, the weight of the block as a part of the weight of the plank, and then they try to solve the question. That is only possible when the things are in equilibrium. This is not a case of equilibrium. Therefore, the n will not be equal to mg. So of course, if I make a equals to 0, alpha L by 4 equals to alpha equals to 0, then the n and mg will be same, but not always. So this is the takeaway from this question. Is it clear? Is this clear, guys?
Yes, sir.
So can you solve now on your own? Tell me the answer. What is the answer coming after solving? So anybody getting the answer for A and alpha?
So once.
says that alpha is equal to 3 by 2 G by L and ACM is 3 by 4 L, 3 by 4 G.
A is how much?
Center of mass is 3 by 4 G.
Alpha.
Alpha is 3 by 2 G by L. By 2L.
Okay. And here can we write the constant here?
Yes, sir.
Yeah, because it's a string and the string is a fixed quantity, so we can add constant. This point will remain at rest. So this is the constant we can add here. Okay. Anyway, so I'm assuming that your questions are correct. So I'm not going to recheck, but I trust you guys. And now I'll go to the one more variety of question that we will come across.
We have to take n 0, right?
Pardon?
Because they will fall independently, na? So normal will be 0.
Why normal will 0?
Because they will fall independently.
Why? If your acceleration, let's say if your free fall acceleration is g, if there is no Planck, then the block can fall with g acceleration. So you have to check that is the point going to fall faster than g.
Okay.
So you need to also realize something very deep. So if you have a rod, and if this point is like hinge, and this is the center, so center of mass from here to here, you cannot have any point in between with an acceleration. This is 0. This is ACM. So any point between this will be less than g. Now somewhere here you will get equals to g, and only beyond certain point we can get more than g. So if the block is kept here, it means it will always have the tendency to move faster than the the Planck itself, and so it will remain in contact with the Planck. Understood? It's difficult. So you will not assume the contact is left with the. Yeah, if the block is kept on the other end on the right side, and if you cut the string, it will fall freely, and the Planck will move even faster than the block. That point. Anyway, so what's the next variety of question that you should know? Okay, we can do questions like this. Imagine we have a question like we have a surface, and we may have a cylinder. Then we have a plank. The radius, this mass is capital M, the cylinder. This is cylinder. This length is L, let's say, and this blank is pulled with a force F, assuming no slipping anywhere. Find ACM of cylinder. Okay, so first step is draw the ABD and try to get some. Okay. You guys can try, then I'll go to the next one. So the friction force on the cylinder will act on the topmost point and bottommost point, right? So at the topmost point, where it will act? Any guess? Because this is the driving force. You are applying force here, so the friction force on the cylinder will support because the friction will try to pull it forward. This is the F1. Let's pull it, and therefore the rod will experience two force: one right due to the applied force, another here left due to the friction Newton's third law. And we know that if you apply force on a disk at the topmost point, it will have alpha much bigger than, alpha are much bigger than ACM. If you remember that friction analysis. So the bottom will try to go backwards. The friction at the bottom will also act forward. Although it doesn't matter, but if you know this, you should apply. So these are the force equation, ABDs that you will see, and then we have normal, of course. And we do have normal here. And we do have gravity also here. So I'm just doing this. And gravity here. Okay, so I have shown all the forces as you can see for Planck separately for block. And then you're supposed to assume the accession of center mass as AC, right? And it will have the alpha this way, and then you can just solve it. So far we have seen the motion of Pulley and all. And now this is the question in which we have connected bodies, and the constant is not at one point, but constant is at 2 points here. One between the plank and the cylinder, another is between the ground and the center. And we know how to write the constant and all. So there won't be too many variables if you just try to analyze and write the laws of motion. If you really understand it, it is easy to solve. So can you solve for AC and alpha? Anybody interested in this question?
Yes, sir.
Okay.
So alpha is equal to F by M plus 2M by 2M into R, and AC means F by M plus 2M. Sorry, capital M plus small 2M.
Okay, so let's write the laws of motion for rod. It is fairly simple. F minus F1 equals to M into A. Now that A is very interesting. It's very easy to find. If you once you choose the accession of center mass as A and alpha, the topmost point we know from the concentration is 2A.
Yes, sir.
So I can just add 2A because the topmost point must accelerate with 2A. Then only it can prevent the slipping. And so we have just only one variable because alpha equals to A equals to alpha R is the constant. So now for the cylinder, the bottom is at rest, so that will be easy for me to just add the torque about the bottom and then get it done. So for cylinder, what I'm doing is, look carefully, I'm writing tau ICR equals to I ICR into alpha. I mean, this part will just simplify all my calculation. And about center mass, sorry, about bottom, the torque is only due to the F1. So I'm done. F1 into 2R is I about ICR, which is 3 by 2 mr square, which is capital mr square. And alpha into R is A. So this we can add as 3 by 2 capital M A. Okay. And therefore the F1 turns out to be 3 by 4 capital M A. And now we are done. Just substitute here. And once you do so, it's very easy. F minus 3 by 4 capital M A is too small M A. And therefore F equals to 3 by 4 capital M plus 2 whole into A, and see this is minus. It's 4F upon 3M plus A plus 1. So things are not very difficult, but you need to be, yeah, you need to practice a lot to actually understand how to manipulate the things very fast and efficiently. So I hope you all have started the practicing from SCR matrix. Are you guys solving SCR?
Yeah.
So now see, there is no end of question. I can keep on solving for the next 1 year, okay, and it will never end. So that's the reality. And as far as the difficulty is concerned, I can raise the difficulty up to 100 times more than what we have done so far. Again, that is of no use. The whole idea is you have learned sufficient, you have the sufficient base to build up anything you want, any difficulty level you want to achieve. From here onwards, it's all about ideas, it's all about your own thinking process. Ideally, the content that should be taught, I have taught more than that, in fact. And I believe that we'll pick up from here and we'll do some great problem solving in rotational dynamics. So I'll start today a new topic because this is done. So I'm considering this part is done. And our next topic is going to be angular momentum. So in physics or in nature, we have few conserved properties, and this property was a conserved property which was realized much later than the other property. So we realize about the conservation of energy as a very intuitive thing long time back, and then conservation of momentum came into picture and the conservation of angular momentum. So what are these quantities exactly? I mean, what they represent in a meaningful way. So I'll give you a detour of angular momentum, like as a practical investigating tool, how it happens in the nature. From there, we'll try to realize what exactly it is and how it controls various natural phenomena which happens. So the core of angular momentum is, of course, inertial, some sort of inertial property. So you spin something and you put on a floor, and then you can see that it spins for a very long time before it falls down, and because of the friction of the surface, it stops. But if we make sure that if it is not going to fall down, so if we somehow make this possible, we do not let object to fall, then probably the air resistance will be very difficult thing to stop. Now, in if you have heard about the figure spinner, which was a craze long time back, I don't know whether it's craze now also. So you spin it and you feel really good about it. I mean, there's something psychological attached to this, and it spins for a fairly long time. So now, the more the expensive this figure spinner, it will have a better quality of ball bearing, which will have lesser friction, and therefore it will spin for a long time. Now, the best figure spinner that was created by the German company, it was very costly and it spun for more than 20 days before coming to rest. So imagine the kind of inertia it was having, and of course the inertia is lost because of the air friction and all. So in an ideal case, there was a very good way to understand the inertia. So what that spinner is doing is it is maintaining its own inertia, and that inertia is preserved, and it is also dissipated very slowly. So imagine that 20 days is long, long time. So it is as good as infinity, like, because we cannot see it something for even 1 minute, and if it is for 1 minute, we say okay, it's lot time. So now 1 minute is lot, then I think 20 years, 20 days is extremely infinite time actually. So every body, when you spin, it will maintain some inertial property that is called the angular momentum. This inertial property we call angular momentum. So the inertial property represents the ability to turn about some axis. And what we are trying to conserve is that what you observe, the ability to turn about some axis, that is always maintained. In fact, every body which is having its linear momentum conserved, by default, it will have its angular momentum conserved as well in most of the cases. The vice versa is not true. So if you say that uh, linear is conserved, so the angular, but if the angular is conserved, so the linear is not true. So what exactly is angular momentum? So if you remember the linear momentum part from the chapter of the laws of motion, center mass, and what I said is that the center mass is moving uniformly because no external force is acting, and the motion of center mass with uniform velocity is manifested by the word conservation of angular momentum. So similarly, if a body is spinning about some axis, and if there is no torque about that axis, then again it will maintain that spin or show the angular momentum. That's simple. So if you have heard that before the, like a long time back, the entire solar system was not there. What we had was a big fireball, and there was sun. Correct? The sun was the biggest fireball. If you remember the some history, maybe not like this. I can do a better fireball. This is your sun, right? It was a big fireball, burning day in day out. And from this big fireball, we got our entire solar system. And in this due process, what happened? We got some planets. So what was happening? Let's try to understand. So in the very beginning, this hot object was spinning very fast. So omega was really fast, really, really fast. And just to consider one part of this fireball. This may be the plant in making. So what happened? The omega was so fast that the gravitational pull on this mass was not sufficient. You may consider the centrifugal force. You may think this way. So gravitational pull was not sufficient to overcome this centrifugal force. So this got detached. But of course, it will not get detached this way. It will get detached tangentially. So to understand this concept, let me do the kind of top view, the flat view of sun. And imagine this is a spin. Try to understand that why uh, we got just 9 planets, not more than 9 planets. What happened exactly? So this part, let me consider this part. And this part is trying to detach. So it will try to detach tangentially like this, if you look from the top. And to detach, you have to move faster than the velocity of this periphery. It means some force will act here on the mass, which will accelerate it further. and that will accelerate it further to give extra acceleration, and therefore this point will leave the sun and will move independently like this. And this in turn will create a force on the sun itself. During the ejection process, the force will be acting on the sun towards the right, and which will create a torque about center of mass, and this torque will slow down the sun. So now omega naught will go to omega 1, the first stage, and because you have just removed the part of it, so this will not take the form of some planet or maybe comet or maybe something, anything. It can, and this process continued till the size of the sun has shrunk to a value which created the tremendous gravitational pull, which prevented the I mean the mass from leaving the sun as a whole. So no bulk mass was leaving the sun because now the gravitational force was good enough to prevent it. The other way of thinking is that omega has decreased to a value that the centrifugal force was not enough than the gravitation. So you can think in both ways. So now the gravity became really stronger than the centrifugal force, and therefore every other mass remained part of the sun for the next billion of years. And every time some mass was leaving the sun angular velocity was slowing down, because you can see every time something is leaving, a torque is acting about the center which is trying to slow down. This force is getting torque about the center, F into, you can say, R. And this torque is slowing down because it's opposite, because omega is this way and whatever is leaving this way is accelerating. So the force on the leaving mass is left, so the force on the sun will be right. And whenever this was happening, the sun was slowing down, and therefore after a long time, maybe after creation of 9 planets, let's assume we have 9 planets still now, the omega really became very small compared to the initial omega, and then that led to the you know uh, from the creation of that led to the uh, stopping of creation of newer planets, and therefore we have limited number of planets in our solar system. Okay, so this entire thing is being governed by something called angular momentum. Now the part which is leaving the planet is also carrying some angular momentum. So the angular momentum carried by the leaving mass from the planet and the remaining planet together is constant. Okay. So if one is gaining some angular momentum, the other is losing some angular momentum. Okay. And that is how they are sharing the angular momentum. They are keeping the angular momentum of the universe as a constant quantity. So in nature, the angular momentum is something like a conserved quantity. And because every planet apply force on each other as a gravitational force, and these gravitational force cannot change the cannot apply the torque on a body, because every gravity or gravitational force acts on the center of mass, or basically we call center of gravity, and therefore they don't create torque and all. So the angular momentum is a conserved quantity in nature by default. The nature will try to preserve its spin. Now, if you want to change it, then you need to apply torque. Just like if the momentum is conserved quantity, and if you want to change it, you apply force. Similarly, angular momentum is by default a conserved quantity, and if you want to change it, you have to apply some torque actually. So just like the absence of force, allows us to conserve the momentum, the absence of torque will also allow us to conserve the angular momentum. So let's say if you take a bat and you just give a spin. Take some object and you just spin it and throw it. Take a coin and toss it. So when you toss a coin, you must have observed that the coin goes up, the coin goes down, but at no point you see that it has stopped spinning while going up. The spinning is conserved, isn't it? So the coin is going up and down, but the motion of center mass is getting affected. It is getting accelerated or decelerated, and it is coming to rest at the topmost point. But in the entire process, if you observe carefully, the spin is not getting affected at all. The spin is always maintained. And the reason is simple: the gravity cannot affect the spin. So gravity having no role to affect the spin, because any force which passes through the center mass cannot affect spin. Spin is only affected by the torque created by the force about center mass. It means if a force can create a torque about center mass, then it can affect the angular momentum, it can affect the spin. But if it is not, then it cannot affect. So now how we realize this concept? Like we need to think of the angular momentum. So it was in the line of the Newton's second law. We came to know about this. So let's say we have a we have a torque equation about a point. So we have a point O. Let me do the origin first. And we have origin. And let me do some hypothetical body. And you apply force submit here. So we have already learned about the torque about a point, correct? So what is the torque about a point? R cross F. So imagine this is a particle, not a body. Imagine the particle is here, M, and at a distance of R. Now it's very surprising that even for a particle, if you apply force, I can define a torque about a point. So this particle may be moving, but I'm just trying to define a force and torque equation about a point O. But how we can add this? We can attack R cross. From Newton's second law, we know F equals to dp by dt, correct? The rate of change of momentum is called force. And this is a very common example. Now what we do is we add 0 to this equation and we call it equation 1. Okay, so what next? So let's write this one. The dr by dt cross p, how much is this value? Do you know? This is also 0. Why? Because the dr by dt is called velocity and momentum is mass into velocity. So m is constant, so v cross v cross product of two same vector is always 0. Okay. So from equation 1 and 2, I can substitute 0. Now that is something very hilarious, that I am replacing 0 by some value. But this one. And the purpose of this entire manipulation is that I can write this as the product rule of differentiation, which you remember that it's a d by dt of r cross p. Now this is something very interesting. So now I'm trying to, I mean, like this is let's say called torque external. That's interesting. And now if you compare with the Newton's second law, which was F external equals to dp by dt. So if you call this as momentum, then if you multiply with something r, we call moment of momentum, correct? If you remember the r cross something,
Yes.
this is called moment of momentum. And because r cross p is called moment of momentum, so this was later on given a name angular momentum. So the name angular momentum was suggested later on, but it was just moment of momentum. The earlier name was moment of momentum. So in the line of Newton's second law, we can substitute this term with some nice symbol, and that nice symbol today we write as capital L, and we call capital L as the moment of momentum. Understood? So this is how we define the angular momentum. I hope it's clear. It is clear, guys?
Yes.
Yes.
Okay. So moment of momentum is not something extraordinary. It's very easy to understand concept. And now what we have defined, you also need to realize it is defined for a point. Now you may ask how point can have angular effect. Yes, every point can have angular effect. If you remember that when we started the circular motion chapter, we were discussing the point, right? A point was moving in a circle. So how can we have angular effect attached to a moving point? And so far we haven't, I mean, talked about the body. So we'll come to body later on. First, try to understand the point first. So imagine a particle is translating on this line. So this particle is translating on this line. Imagine with some velocity u, mass is m, and then imagine that there is a person standing here, observer. So you can see that the observer is sitting on the line of motion of the particle. So now if I ask you that for this observer, do we have any angular effect for this particle? Will you see this particle to be turning right or left?
No, sir.
The answer is no. It means for this observer, there is no angular effect associated. But imagine another observer who is somewhere here. Right now, this guy is exactly below the object. But at the very next instant, this line joining the object to the observer will keep on changing the direction. You can see. So the line of observation, this is called line of so as the particle will move, the line of observation will start changing the orientation. So there is an angular effect associated with the motion of particle and the observer, correct? So it is the same object, but in the perspective of two different observer, things are quite different. So in the frame of the observer number 1, there is no angular effect associated. But in the frame of observer 2, although you are moving on a straight line, but the line of observation is turning. In a way, there is a turning effect associated. And therefore, we say that although the particle is having the momentum, but for the observer 2, it will have some angular effect, and we can call that effect as angular momentum. And it is very easy to calculate. This angular momentum is very easy to calculate. So the first is by definition. So the angular momentum is a frame dependent, correct? It means not all observer will have same answer. Do you realize this? Not all observer will have same answer. So observer 1 will have 0 answer, but the observer 2 will have non-zero answer. And we're trying to understand what will be the answer. So it is fairly simple to analyze this situation because the particle will have in general distance r, particle have in general momentum mu, and let's call this the distance between the observer and the line of motion as d. So d is called the perpendicular distance. I'm just taking it d. Now the r vector is drawn something like this, and if this is theta, then I can say this is also theta, correct? So you can see that the r vector and the momentum vector is making some angle, let's say 90 minus theta this time. By definition, the angular momentum associated with the, let's call it O, the angular momentum of this particle associated with the O point is R cross P by definition. This is by definition. And this we can write as a, in scalar form as LO equals to RP sine theta, where this is by definition of cross product. So the L naught is RP sine theta. And if you apply this formula, what will you get the answer? R is R, P is mu, sine is sine. And what is the angle between the R and mu? I think it is 90 theta, correct? This is the definition of cross product. It is not the theta which I have used in the diagram. This is the theta of definition, which is the angle between R vector and P vector. Okay. So now, if you just simplify this part, you will get mu R cos theta. And anybody who realize what is R cos theta? R cos theta is D value.
D.
So now you can see the answer is pretty simple. It is MUD, mud. Okay. It means the angular momentum of any particle performing the translation is given by the product of momentum and the perpendicular separation between the momentum vector and the point of observation. So the line of motion and the point of observation, so if this is the line of motion, and if you're observing from here, what will matter is this distance, that's it. And that is why the moment you come to the line of motion itself, your distance becomes 0, and therefore you fail to see any angular effect. So there are many ways in which you can realize this part. So the other way is this one. Let me do a separate diagram. So you can again understand what is the actual meaning of angular momentum. It is the rotational effect or angular effect that the motion
So,
creates in the frame of an observer. So angular momentum is not something angular. It is like the observational effect actually. So if I observe something, let's say, if you remember, yeah, I mean, I do remember one of my very common experience that when we travel by the train, and if you look at the any field and all, you can see the it looks like the trees are turning. If you have observed, so the surrounding trees which are quite far looks turning. So if something is really close, it looks going backward. But if something is really far, it looks turning. Have you observed this?
yes, sir.
Yes, sir. Yes.
Yeah, because everything in a frame of yours is going backward, and therefore, because you are quite far from them, you feel the turning effect. But when it is very close, you don't feel the turning effect. You feel it's going backward. Correct? What does it mean that if this is the bus and this is a very close object, so you will see it's going backward because the d is very small. But if it is really far, you will see that it's turning something like this. You can feel the turn, the rotational effect. You can will give you the rotational sense, and anything which is very closer to you, it will give you the translational sense. So in a way, because you are moving, so in your frame they are moving. So if they have the velocity, and if you are an observer, and if they are quite far from you, if d is really big, then the angular effect will be a dominating feature, and therefore, and that is why we see things turning. Okay, so this is the a very common observation. How many of you have observed this? I think all of you.
Yes.
Okay. The other way of observing this same question is, so let's say the observer is here at a perpendicular separation from the line of motion D. Always remember the D represents the separation from the observer to the line of motion. And this is moving with velocity u. Maybe after some time this particle is here, and for the given observer this particle is here at a distance r with momentum mu, and we have done this exercise many times. Okay, this time I'm going to change the angle the way I have taken. So let's, because this is er, let me take this as theta because that will be easy for you. Now this mu we can resolve into two components, one along the er and one along tangential
Perpendicular
axis,
to E.
perpendicular to er. So this we can write as, the momentum in this direction will be how much? Mu sine theta, and the momentum in this direction is how much? Mu cos theta. Correct? And now I think this is a very obvious question. Which component will give you the turning effect? The
Mu
sine
sin
theta or the
theta.
cos theta? Definitely, because that's a circular motion exactly. And therefore, the angular momentum is the momentum which gives you the turning effect, something which can change this angle, alpha. So if alpha is changing due to this component, it means that is the component which will impart the angular effect. So what I can say that angular momentum about O is nothing but the product of that component of momentum which gives us turning effect. So I can just write mu sin theta into how far is that from the O point. So now I can choose this as a line of motion, and then I can see that for this line of motion, R is mutually perpendicular, and that's why I can multiply this with R, because mu cos theta will have anyway no contribution. So these are two different, like, aspect of thinking. In one case, I resolve the R perpendicular to the line of motion vector. In this case, I have kept the R as same, and then I have resolved the momentum perpendicular to R vector, and the product of these two will give you the value. And again, this is mu into R sin theta, and we know R sin theta is going to be D. At the end, it is mu D, okay, or dum, but this is nice, mu. So the angular momentum is not only meant for the bodies, it is meant for any point mass as well. But for any point mass, we must have some predefined observer with respect to which you want to express the angular effect. So the angular effect is not something always absolute. It could be a frame dependent. So we may have some angular effect in one frame, and we may not have the angular effect in some other frame. So as you remember on the previous page, what I said, that for observer 1 there is no angular effect, but for observer 2, yes, there is angular effect. So you need to realize that what is the angular momentum? It is the angular effect created by the moving mass with respect to some observer. Okay. Now angular momentum is due to particle, due to body, and due to everything. Now there is something called spin. Now spin is not frame dependent. That we need to realize, that spin is defined for a bodies, something with dimension. So spin is not for particle. You need to understand, spin is entirely a different concept. So rotational effect is one idea, and spin is the another idea, and we should not confuse between the two. So spin is a property of a body itself. It's a unique property. Angular momentum is not a unique property. Angular momentum is the angular effect that you can produce, and any particle can produce the angular effect. And that's why the angular momentum is about angular effect, and spin is something very unique to a body. It's a unique property to a body. So when we say every planets are spinning on their own axis, that is their property, and the spin has nothing to do with the observer. Okay, so observer defines angular momentum, but spin is nothing to do with the observer. It is something unique, and it is unique for everybody. Okay, for particle we do not consider spin. Spin is only considered for bodies with finite dimension. Okay, so every planet will have spin, and no particle will have spin. So particle is the concept. So as long as we are defining particle, then we cannot define spin, and that will have the very far-reaching consequence, that in case of KTG, the kinetic theory of gases, if you remember, for a single particle, like every gas molecule, we assume there is a particle, and therefore for monoatomic gas there is no spin associated, and because of the lack of spin, they don't have the rotational degree of freedom. So for every monoatomic gas, we only consider the translation or translational degree of freedom. But the moment you become diatomic, you become two as a whole, one object. And because you got dimension, which is the separation between the two particles, which is like your dimension, and therefore you start exhibiting the spin property. And therefore I can choose two axes about which your spin is non-zero, and therefore you have the two rotational degree freedom. And the moment you become like three-dimensional, like two-dimensional molecule, you're not a linear molecule, you're a non-linear molecule. then I have to associate 3 axes for your spin. And so you get the 3 rotational degree of freedom. So when we have a linear molecule, a molecule with one line is the shape is linear, then the rotational degree of freedom is only 2. The moment you become non-linear, your rotational degree of freedom becomes 3. So similarly here, angular momentum is for everyone, but spin is not for everyone. Angular momentum is for particle and body, spin is for body, not for particle. So later on we'll come to know what we just calculated, what we call it. So there is a name for this, and it's a very famous name. So the angular momentum which is associated with the particle is called orbital angular momentum. So in physics we have 2 types of angular momentum, orbital and spin. Spin is unique, it is frame independent. This is frame dependent. This is for bodies only, but this is for particle and body. So this is basically for particle, but in case of body, only center mass we take as a particle, and then we describe the orbital. So we define orbital for a center mass, and we define a spin as a separate property. Every body in nature, every body in nature will have 2 types of angular momentum, one frame dependent called orbital, one frame independent called spin. Every particle will have, or not will have, every particle may have orbital angular momentum depending on the observer. So if the observer is on the line of motion, then there is nothing, there is no angular effect, so there is no orbital angular momentum. Okay, so this distinction I will make it more clear in this topic of angular momentum of a rigid bodies. Right now we are learning the angular momentum of a particle, and we are just trying to understand that is it possible for a particle to have angular effect? The answer is yes. For a particle can also have the angular effect. It is all about the way you observe it, and that's why the O is clearly saying that it's a frame dependent quantity. It's not something absolute. So we'll divide the entire journey into 2. This angular momentum into 2 parts, 2 category. And if you remember one more thing I can recall, that if you remember the Bohr's postulate, in that you consider the electron as a particle moving in the orbit, correct?
Yeah.
Yes, sir.
Yeah.
The electron was moving in a particle, so the angular momentum associated of that electron with respect to the center of the orbit is mvr.
Yes,
And that
sir.
was nothing but the orbital angular momentum, because what you're trying to write is you're trying to multiply the momentum with the perpendicular separation from the center of the orbit. And how far you are from center? R away. So that's why your angular momentum was mvr. Mv is the momentum and r is the distance from the center mass. But there you never consider the spin. It means the electron also spin on its own axis, and so it will have its own spin angular momentum, which is the 4th quantum state, S. When
Yes, sir.
so
Minus half and half.
correct, minus half. So what is minus half and half? It's the relative angular momentum, spin angular momentum of some quantized quantity. So we have something quantization of angular momentum, and spin is a different calculation, and orbital is a different calculation. So if you remember that we consider spin separately and we consider the orbital separately. Okay, so these effects are very important in learning some deep concept of physics, like a concept of ferromagnetism. So you might have heard about the ferromatism, but the ferromatism is associated with the spin property of electron, whereas the paramatism and the diametism is associated with the orbital property of electrons. So the orbital motion gives rise to the property like paramatism or diamatism, but it is the spin which is the very cause behind the ferromatism. So something this is still a mystery, but the ferromatic property is mostly attributed to the spin property of electron, not due to the orbital property of electron. So those things are really deep. So you need to understand certain things in bits and pieces. Like angular momentum is a study about angular effect, and the angular effect of course can be created by the spin, but angular effect is also created by the orbital motion, or you can say by observer based motion. So when I say orbital, it's like observer based motion. So m, when you write in Bohr's postulate, when you write mvr, you're not writing angular momentum, you're writing angular momentum with respect to the center of orbit. Now this is something which everyone ignores. So we remember mvr, but we never think that about which axis, about which point this is answer. So mvr is the answer about which axis? The axis passing through the
Center of
center of orbit. Center of orbit. mvr, in mvr, the r is the distance from the center of orbit to the particle, correct?
Yes, sir.
So this is the idea. I mean, you need to understand. You need to understand that the concepts are fairly different or distinct flavor. I mean, these are distinct flavor of angular momentum, and both are different. Like one consideration and other have no relation. So spin is something very unique. I mean, we'll talk about more about the spin in a while. Okay. So angular momentum calculation is pretty easy. Now let's talk about the direction. How to find the direction of angular momentum? It's very easy. Just look at the sense of rotation. So I can see that because as the particle will move towards right, the line of observation, if you remember the sentence I used just a while before, line of observation, correct? So tell me, the line of observation is turning clockwise or anti-clockwise?
Clockwise.
So the direction of L0 will be the
Clockwise.
sense, yeah, the direction of L0 will be taken in the sense in which the line of observation is turning. So line of L0 will be in the sense in which the line of observation will turn. And because it is clockwise, so I can, if I choose this as xy plane, then I can say clearly that the direction of L0 will be minus k cap in this case. Because minus k cap means inward, right? Clockwise means into the plane. Okay. So yes, the angular momentum will have a direction, and the direction is pretty simple. And if you want to get the direction by the definition, you can write r cross p, and r is a vector which is always from the observer towards the object, because the observer is the origin, so the r is away from it. So r cross momentum vector p, if you use the right hand thumb rule, it will be inward. Is this clear? So r cross p is going to be inward. Okay, so what next? What we can write next? Hello, hello. Am I audible, guys?
Yes, sir.
So let's do one or two problems before we go to the next concept, which is angular momentum about an axis. So we have seen the angular momentum about a point. Now we'll see the angular momentum about an axis in a while, but let's do some numerical. So let's say this is xy plane, and what we have is a line. This is a comma 0. This is 0 comma b. And there is an observer at the origin. So now we have a particle of mass m, and it is following this line as a line of motion with velocity u. Question is, what is the angular momentum about the only the value? So how much turning effect this particle will have for the observer sitting at the origin? That's the question. So if I am the observer looking at the particle sitting at the origin, then what is the turning effect I can feel? So you are supposed to only use the formula MUD, and D is the perpendicular separation from the line of motion, and this D is very famous. We have done 1,000 times, and that's the answer. Those who know the mathematical, okay, those who know mathematics a bit, if I give you any line and if I tell you that the equation of this line is y equals to mx plus c, and if I give you some random particle moving here, it's all about mathematics, how much you know mathematics. And let's say velocity is v, mass is m, and then there's a point here, who is the observer, having coordinate a comma b, and what is LP now? Numerical value. What is LP?
Yes, then. Just 1 second.
Okay. Now I can leave.